Hey everyone, welcome to today's Explainer. If you're studying computer architecture, you know it's not just about slapping more transistors on a piece of silicon anymore. Today, we're treating this entire topic as an active design challenge. We're going to get under the hood, look at the physical realities, the massive engineering hurdles, and, honestly, the math that makes modern computer architecture tick. Because making a computer genuinely fast, man, that is one intricate balancing act. I want to start off with a quote straight from the textbook that absolutely nails it. Processor designers must come up with ever more elaborate techniques for feeding the monster. I mean, what a great way to put it. Thanks to Moore's law, chip makers have been able to give us chips with 4 times as many transistors every 3 years. But here's the catch. That mind-boggling raw processor speed, it's completely useless if the chip is starving for data. If it doesn't have a constant stream of instructions ready to go, all that raw power is just sitting there wasted. And trust me, nobody wants an angry, starving processor on their hands. So here's our roadmap for this explainer. We'll start with feeding the monster, then move into performance balance, dive into the laws of performance, tackle the math of means, and wrap it all up with benchmarks. Let's get right into it. Section 1, Feeding the Monster, specifically looking at microprocessor speed. Okay, let's dive into this first major architectural challenge, keeping our data-hungry processor constantly busy and well-fed. To keep that processor from stalling out, designers have to use a whole arsenal of tricks. First up, we just overlap tasks. Pipelining works kind of like an assembly line, right? And superscalar execution takes it a step further by issuing multiple instructions at the exact same time. Then, things get a bit more clever. We get predictive. Branch prediction literally guesses what code is coming next, while speculative execution takes that guess and actually executes the code ahead of time just in case we need it. Add in data flow analysis to schedule everything efficiently, and you've got this incredibly elaborate dance, all designed to prevent even a microsecond of unnecessary delay. That brings us to Section 2, Performance Balance and System Bottlenecks, because here is where we hit a serious wall. While processors were racing ahead at these breakneck speeds, other critical components, like main memory and your I/O interfaces, were lagging pretty badly. This created a severe system bottleneck. You see, the interface between the processor and main memory is literally the most crucial pathway in the entire computer. If memory can't keep pace, the processor just stalls out in a wait state. We desperately need performance balance. What's really interesting here is the dramatic shift in these historical processor trends. If you trace the data for frequency and power, you'll see something wild. Traditionally, we just brute forced performance gains. We jacked up the clock speed and packed in more logic. But right around 2004, those metrics hit a literal physical wall and totally flattened out. Why? Because of heat. Power density got too high, and we hit something called RC delay. The microscopic wires between transistors got so unimaginably thin and so close together that resistance and capacitance were actually slowing the electrons down. Designers couldn't make a single processor any faster without literally melting the chip. So the industry had to make a massive pivot to multi-core chips. Moving on to Section 3, the laws of performance and the mathematical tools we use. So we shifted to multi-core and parallel processing, but how do we actually know if those parallel solutions work in practice? We need a reality check. First up is Amdahl's law. Coined by Gene Amdahl way back in 1967, this law provides an absolutely crucial reality check. It basically says that speeding up one part of a system doesn't just magically speed up the whole thing equally. Specifically, the potential speedup of a program running on multiple processors is fundamentally limited by the fraction of the code that is inherently sequential. In other words, the parts of the program that absolutely positively cannot be done in parallel are always going to hold you back. And the math here brilliantly illustrates that limitation. While the formula calculates your exact speedup, the real story becomes obvious when you graph it out. The different trend lines represent F, the fraction of the code that can actually be parallelized. Think about a scenario where 50% of your code is parallelizable. Notice how your total overall speedup maxes out at just 2x? And that is even if you throw 1,000 processors at it. It's wild. As you add infinite processors, your speedup faces brutal diminishing returns, all bounded by that stubborn sequential portion of the code. So you might be wondering, are these conclusions just way too pessimistic? Well, the textbook points out that some folks definitely think so. Modern server and database applications, for instance, can often handle massive parallel threads perfectly. They can execute multiple client tasks at the exact same time, pushing right up to the theoretical limit of the processors. But having said that, Amdahl's law still stands as a stark warning. It highlights the immense difficulty of writing highly parallel software. Because at the end of the day, if the software isn't specifically adapted for it, all those extra cores you paid for are just going to go to waste. Okay, our second mathematical reality check is Little's law. This is a fundamental queuing equation. It states that L, the average number of items in a system, equals the average arrival rate of items, which we call lambda, multiplied by W, the average time an item actually spends in the system. Now, why does this matter to you as a system architect? Well, it's incredibly relevant today for tracking multi-core bottlenecks. Imagine you've got multiple threads all needing to grab data from shared memory at the exact same time. They literally have to wait in a queue. Little's law helps architects mathematically model these queues to ensure that we're actually meeting user requirements without causing massive, frustrating delays. Section 4, the math of means, and how we go about summarizing our results. Because now we need to shift from theoretical laws to how we actually calculate test results fairly across completely different systems. So, the crucial point here is how important it is to choose the right mathematical mean. When you compare the numbers, notice how if we use the traditional arithmetic mean, dataset D looks like the clear winner with a score of 7.55 compared to 7.00. But if we switch to the geometric mean, suddenly dataset C is the higher one, 6.68 versus 6.42. Why does this matter so much? Well, in performance testing, the arithmetic mean can be heavily skewed by just one or two extreme outlier values. The geometric mean, on the other hand, gives proportional weight to all the values in a dataset. It's so much better because it provides consistent, reliable results when you're trying to measure the relative performance of two completely different machines. Which brings us to Section 5, benchmarks and measuring actual systems. This is where the rubber meets the road. Because raw clock speed doesn't actually tell us how a processor is going to handle a real-world application, the industry relies on standard benchmark toolkits. The big one you'll hear about is the SPEC CPU 2017 benchmarks. This is how we answer the ultimate question, okay, but which machine is actually faster? But when you're looking at these benchmarks, you have to distinguish between two totally different metrics. The speed metric is exactly what it sounds like. It measures the time it takes a computer to complete one single compiled task. But then you have the rate metric, which measures throughput. Basically, how many tasks can this system accomplish in a given amount of time? The rate metric is where a modern system really gets to flex its multi-core muscles, executing simultaneous tasks across all of its available processors. So, we've seen how we feed the monster, we've seen how we hit the thermal power wall, and we've explored how multi-core design is strictly bounded by Amdahl's law. So I want to leave you, the future system architects of the world, with a slightly provocative question. If Amdahl's law dictates that we'll eventually face diminishing returns from just slapping more and more cores onto a chip, where will the next massive leap in computing performance actually come from? How are you going to break through the next physical boundary? Keep that in the back of your mind as you continue your studies. Thanks for tuning into this explainer.